Maximize. Share. Double. Right. Right. Sure.
Good afternoon, everyone. I'm Shashikala, working on the ionosphere of inner planets under the guidance of Dr. Kamsali Nagarsan. I'm here to present my half-yearly progress report from 1st July 2024 to December 30th December of 2024. My proposed research topic is a comprehensive study of ionospheres of the inner planets. Here, the left side of the background picture is the sun, which is emitting solar flakes, and the right side is the terrestrial planet. Here, inside the sun's core, nuclear, because of intense heat energy and pressure, a nuclear fusion process takes place, which releases such nuclear fusion process generates massive amount of energy and allow it to move towards its outer surface. So once the electrically charged hot plasma move towards its outer surface, it creates a magnetic field. Create magnetic field, and when a such a strong magnetic field twist and tangle upon time, it gives rise to a burst. It gives rise to a intense energy in the form of a light or heat. That itself we call it as solar flare. The movement of such electrically charged hot plasma is a solar storm which is moving towards the Earth's magnetic field, where the ionos where the ionosphere of the different planets get disturbed due to the solar radiations coming from due to the solar radiations coming from the sun. These are the contents of my presentation. During this 6 months period, I've gone through research papers, articles, and journals related to my research topic, and I've attended short course on solar physics conducted by PRL. I've attended a short course on solar physics conducted by PRL of Department of Space, Ahmedabad, during September 2024. And I've engaged in regular discussions with the faculty members of physics department and also with the research groups. During this period, I've submitted Form C and synopsis on my proposed research topic. Sir?
Minus.
This picture shows the four inner planets. The four inner planets are Mercury, followed by Venus, Earth, and Mars. These inner planets are also called as terrestrial planets because of the rocky and solid surface, and they are found to be smaller, massive, and closer to the Earth, closer to Sun. Actually, they have arranged not on their sizes, but arranged according to the distance from the Sun. This is the Mercury. As we all know, Mercury is the smallest and innermost planet of our solar system. The Mercury has a weak magnetic field. It has got weak magnetic field, and its atmosphere is found to be very thin. Hence, its ionospheric layer is less dense, and having and its electron density concentration in such ionospheric layer is found to be extremely low. Mercury's ionosphere contains ionized atoms which include sodium, potassium, calcium, oxygen, etc. As we know, the Mercury is closest to the Sun. Its ionosphere uh, uh, is directly affected by the solar radiations, which in turn disturbs its structure and the dynamics of the layer, ionospheric layer. Next is Venus. We know Venus is the brightest of all planets. Venus atmosphere is very thick, which is dominated by the carbon dioxide, uh, and its magnetic field is weak. Its ionospheric layer is because of thick atmosphere. Its ionospheric layer is dense during daytime and thinner during the night time. Like Mercury, since it is very near to the Sun, it is affected by its ionospheric layer get affected by the solar radiations. The Earth's atmosphere. I'm going to explain the Earth's ionosphere in the next slide. And this is the Mercury. This is the Mars. We know Mars planet is also called as red planet because it is covered with iron oxide. Mars atmosphere is very thin compared to that of Earth. So its ionosphere is found to be thin compared to that of Venus. Like the other planets, the Mars also get affected by the solar radiation. This picture shows the Mercury's exosphere and ionosphere interaction with the solar wind. Mercury has a weak, as I mentioned earlier, Mercury has a very weak ionosphere due to its thin exosphere and lack of substantial atmosphere. The ionosphere is mainly formed by the interaction of the solar wind with the surface materials, which creates ions like sodium and oxygen. This image is taken from NASA's Messenger mission, which shows the Mercury's magnetosphere and ionosphere. Mercury lacks dense atmosphere, but the solar wind is directly impacts its exosphere, which leads to ionization. The next inner planet is Venus, which has a well-defined ionosphere, which is dominated by carbon dioxide and oxygen ions. It interacts strongly with the solar wind due to the absence of global magnetic field, which leads to the formation of an induced magnetosphere. This image shows the Venus ionosphere and its interaction with the solar wind, which is taken from the ESA Venus Express mission, depositing the ionospheric layer. The solar wind interaction with the thick Venus ionosphere leads to the loss of ion loss into the space. Next is Earth. The ionosphere is divided into three regions like D, E, and F regions, and it is mainly influenced by solar radiation, geomagnetic activity, and atmospheric waves. It plays a crucial role in radio communication and space weather. This image shows the Earth's ionospheric layers and their electron density profiles. Density profile during a solar storm. Earth's ionosphere responds to geomagnetic storm, which creates auroras and radio wave propagation effects. The last innermost planet is Mars, which has thin ionosphere, mainly composed of oxygen and carbon dioxide ions. It is mainly influenced by solar radiations and lacks global magnetic field, which leads to the direct interaction with the solar wind. The image shows the Mars ionosphere and its interaction with the solar wind. The image is taken from the NASA's MAVEN mission showing ionospheric escape processes. Here, the solar wind strips away the ions due to the Mars. Because of Mars' weak magnetic field, solar wind strips away ions, which leads to the gradual atmospheric loss. This image shows the different layers of atmosphere, where the ionosphere lies in the region within the mesosphere and thermosphere, which extends from which starts from 50 kilometer and extends up to 1000 kilometer. The three different layers of Earth's ionosphere are D, E, and F region. This D region starts from 60 to starts from 60 kilometer to it lies between 60 to 90 kilometer. The E lies between 90 kilometer to 150, and F region starts from 150 kilometer. Yeah. As we all know, the solar radiations that are coming from the sun, once they interact with the atom and the molecules that are present in the thermosphere, they get ionized and produces positive ions and free electrons, which forms electrically charged layer called ionosphere. Here, the central portion of this picture shows the electromagnetic radiations that are coming from the sun. The X-rays having wavelength in the range 0.01 nanometer to 10 nanometer get absorbed by mesosphere. Extreme UV and far ultraviolet radiations having wavelength from 10 nanometer to 200 nanometer, they get absorbed in the upper atmosphere. The middle ultraviolet radiation having wavelength from 20 nanometer to 300 nanometer, it get absorbed in the mesosphere, whereas near infrared and visible and IR radiations, they get absorbed. They get absorbed in troposphere, or they reaches the tropospheric layer. The right part of the picture represents the ion density, variation of ion density with respect to the altitude. Here, the red color profile indicates the electron density. Green is oxygen molecule density. Then blue N2, and yellow color profile indicates oxygen atomic oxygen. Here, as altitude increase in the D region, as altitude increases, with respect to increase in the altitude, the ion concentration also increases and in D region, the electron ion concentration increases and become almost constant, whereas blue and yellow, whereas N2 and oxygen atom ion concentration increases with respect to increase in the altitude and become almost constant. Then oxygen molecule increases and become constant. The left picture of the image indicates it represents the temperature temperature profile, starting from the troposphere. In the tropospheric layer, the temperature decreases till it reaches the tropopause. Beyond tropopause, the temperature increases. Temperature increases. Then once the mesosphere starts, its temperature decreases and increases in the thermospheric layer. In the solar maximum period, that is during the period during which the sun is active, consisting of a large number of sunspots, the temperature is found to be extremely large, which is found to be around 1200 Kelvin. And in the solar minimum period, that is solar minimum period is the period during which the sun is less active, consisting of less number of sunspots, solar wind, and solar storm. The temperature is found to be less, which is found to be around 800 kilometer. As I mentioned earlier, the picture shows the three different layers of the Earth's ionospheric region. Here, the D region it appears only during daytime, whereas E and F region appears during day and also in the night time. This D region it absorbs the high frequency radio waves and reflects the low frequency radio waves. Whereas E and F regions they absorb low frequency radio waves and reflect the high frequency radio waves, which is responsible for long distance communication, especially with respect to the F region. In F region, both F1 and F2. F region is divided into two layers, F1 and F2 during daytime. But in nighttime, we can observe only F2 layer. This F2 layer is mainly responsible for long distance communication. This is about the different layers of the Earth's atmosphere. Next is about the objectives of my research work. I've listed the objectives of my research work, which are as follows. The main objective of the research study is to understand the ionospheric composition and ionospheric density of the terrestrial planets. Why? Because these ionospheric composition and its and the ionospheric density varies from where it is found to be different for different. It is found to be different in different terrestrial planets. So my research is mainly focuses on the better understanding of the ionospheric composition and density. And the next objective is to understand the variation in the temperature of terrestrial planets due to solar heating. This is because due to the solar heating or due to solar change in the solar radiation, the temperature of the terrestrial planet it varies. So which is mainly so it is a necessity. It is necessary to study the variation of temperature of different terrestrial planets, which is required to study the ionospheric characteristics. Then the next objective is to study the physical processes governing ionization, recombination, and energy transfer. We know in ionospheric region, ionization takes place where once the electromagnetic energies get absorbed by the atom or the molecules of the ionosphere, they get ionized and electrically charged layer is formed, which is nothing but the ionization. So this ionization mainly takes place. It takes place mainly due to the solar radiations. Once the atom it absorbs sufficient radiation from the sun, the electrons in it get knocked out, and they create. Because of this, the loss or gain of electrons, loss or gain of ion takes place. So that's the reason why the ionization of molecules takes place, and recombination is this recombination process takes place during daytime because of the absence of sunlight, and here the transfer of energy takes place. So to study, so the research focuses mainly on the better understanding of these processes. And also, my study focuses on the comparison of the ionospheres with respect to the different terrestrial planets. These are some of the These are the objectives of my research study. Here, I've taken a graphical representation of the dayside ionosphere of the three inner planets like Earth. The first graphical representation, it shows the dayside ionosphere of Earth, and the second representation is with respect to the Venus, and the last one is with respect to the Mercury. Here, these graphs shows the variation of number density with respect to the altitude. Here, the electron density, the black color profile, it represents the electron number density with respect to the altitude. As altitude increases, the number increases, the number density also increases, and number increases. Similarly with the other ions, but with respect to the atomic oxygen, as the altitude increases, the number density also increases, and it becomes maximum around 300 kilometer. The second one is Venus graphical representation of number density. Number density with respect to the altitude of Venus ionosphere. Here we know that in Venus atmosphere, carbon dioxide is that atmosphere is mainly dominated by the carbon dioxide. The green color profile, it indicates the CO2 number density. So as the altitude increases, the CO2 concentration increases and decreases with respect to the increase in the altitude. And the last representation that is with respect to the Mars. And this picture shows the temperature ionospheric electron density profiles of the inner planets. The red color, blue color profile, it represents the ion concentration of the Earth. So here, as altitude increases, the electron density also increases. Then decreases with respect to the decreases with respect to the increase in the altitude. And we know the Mercury. Mercury has weak and transient ionosphere with low electron density. So, as the altitude increases, the electron density it increases to a lesser extent and decreases with respect to increase in the temperature. Venus and Mars. The profile of Venus and Mars are almost same. The peaks, the single layer ionospheres peaks around 150 to 200 kilometer. The peak of both the profiles lies between 150 to 200 kilometer. During this period, I've made some literature survey and I've listed some of them here, along with I've highlighted some points with respect to each of the paper. In the first paper, it suggests that all the important gases that are found in the upper atmosphere of terrestrial and Jovian planets have ionization threshold in the range 10 to 16 electron volt. and photons with the shorter wavelength of around 120 nanometer. That means all the prominent gases that are found in upper atmosphere, all the prominent gases to get ionized, they require a minimum threshold voltage of around 10 to 16 electron volt, and with a photon with a wavelength of 120 nanometer. The sun's irradiance in extreme ultraviolet and soft rays, X-rays, exert direct control of photochemical processes in the terrestrial ionosphere, which takes place over time scale from minutes to diurnal, months and decades. The other paper, the paper comparative study of ionospheric response to the solar flares at the different terrestrial planets says that the ionosphere of the terrestrial planets respond greatly to the enhanced X-ray and extreme ultraviolet radiations during solar flares. And it suggests that during solar flares, the inner planets, they react strongly to increase X-ray and ultraviolet radiations. And it is found that on September 6, 2017, electron density increases in the lower ionosphere of the Earth's planet, but this amount change is found to be different for different inner planets. And it also suggests that the ion temperature at especially at Earth and Venus share a similar response to the flares, but it is found to be different in Mars because of its unique atmospheric conditions. The other paper it suggests that the carbon dioxide dominated thick atmosphere of Venus coexist with an ionosphere which is mainly formed on day side via the ionization of atmospheric neutrals by extreme UV and soft ray photons. Venus contains it also highlight that the Venus contains an ionosphere that should be in many aspects. It resembles the Mars ionosphere, as both planets possess carbon dioxide dominated atmosphere with a similar neutral composition. And the other paper that is the solar system ionosphere. According to this paper, the very basic processes like such as the ionosphere, chemical transformations, etc., are analogous in all the ionospheres. The major difference are the results of factors such as different neutral atmospheres, intrinsic magnetic field strength, and the distance from the sun. And also highlighted that the improvement in the understanding of any of the ionosphere in our solar system helps to control the physical and chemical process in all of them. The methodology what I'm going to adopt in my research work are as follows. Here the data are acquired from the space missions and satellite. For example, for Venus, Venus or for Mars, we can get the data. We can acquire the data from the various missions like Messenger. Not Messenger, Venus Express, Mariner 10, etc. So once the data is acquired, the data can be analyzed using ionospheric profiles, which includes temperature, composition, and electron density. And it can also be analyzed using observational and simulated data. The data can also be analyzed by comparison. So the data can be analyzed by comparing the ionospheric properties and processes across different terrestrial planets. So with this, I conclude that for atoms or molecules to get ionized, the gases require a minimum threshold energy of around 10 to 16 electron volt and wavelength below 120 nanometer. Then during solar flares, the ionospheres of the different planets react strongly but they're found to be different due to their unique atmospheric conditions. And though the fundamental process like chemical reactions, ionization process, etc., are common across all the planetary ionospheres. But there is a variation in the atmospheric composition, magnetic field strength, etc., which results in the distinct dynamical behavior. Thus, improving our understanding of ionosphere of any planet helps us to understand the physical and chemical processes which affect all the ionospheres in our solar system. These are the references.